Hello students, today class we are going to discuss the significance of Schrodinger wave equation. This is the most expected long answer question from the quantum mechanics. Here, according to quantum mechanics also called as wave mechanics, because according to quantum mechanics the particle is considered as wave. Here, according to quantum mechanics there is no distinction between the particle and wave. So here they are considering electron can move as particle and as well as a wave, and usually the system can be described by a mathematical function that is called wave function psi. So basically what is mean by Schrodinger wave equation? It's derived a second order differential equation. It is actually a derived second order differential equation. What it actually give information? This is a second order differential equation, and this will describe about the wave motion of electron which actually propagating in the three-dimensional xyz axis. What is the equation? The equation is dou square psi upon dou x square plus dou square psi upon dou y square plus dou square psi upon dou z square plus 8 pi square m upon h square e minus v psi equals to 0. This is actually a second order differential equation. This is our Schrodinger wave equation. So this is actually a time independent Schrodinger wave equation. Here there is no time term, right? So this will give many solutions, and this is also will give information about lot of information about electrons. And basically the Schrodinger wave equation derivation is there in our part. So today we are going to discuss about the derivation of Schrodinger wave equation. So this is helping to find the particle energy in one-dimensional and as well as two-dimensional and three-dimensional box also. This derivation of Schrodinger wave equation, the first thing we should know before deriving the Schrodinger wave equation, here suppose we have to imagine a particle that can be electron or anything. Let this electron is having a mass m and it is moving with a velocity v, and imagine it is having a kinetic energy that is T, and it is also having potential energy V. So what is this one? Imagine the particle electron is having mass m with velocity v, and it is having kinetic energy T and potential energy as V. In that condition, so the total energy of the particle will be the sum of the kinetic energy plus potential energy. So usually we know that the kinetic energy T must be equals to half mv square, right? So if you are multiplying the both numerator and denominator with mass, so there will be no change, right? So you can multiply with mass m. So what it will happen? So mv square, if you multiply both numerator and denominator, so it will give m square v square upon 2m, right? The T will come as m square v square upon 2m. So imagine this is the equation 1, that is total energy must be equals to the kinetic energy plus potential energy, and in that the kinetic energy T will be equals to the m square v square upon 2m. So here the mv, what is mean by mv? So we know that the momentum P can be written as mass multiplied with velocity. So you can replace this term mv with P square. So I can replace the T is equals to the P square upon 2m. So the T can be written as P square upon 2m. So consider this is equation 2. So what is mean by P here? The P is actually a total momentum of the particle. What is mean by P? The P actually total momentum. Total momentum in the sense you have to consider the particle momentum in terms of x-axis and as well as y-axis and as well as z-axis. So if suppose the particle is oriented in x-axis, so the momentum can be represented with px. If it is y-axis, can be represented py. If it is z-axis, pz. So the total momentum always is equals to the combination, that is the addition of. So p square can be replaced with px square plus py square plus pz square. Why? Because we are going to describe the energy of the particle in three-dimensional axis. So that's why we must have to consider all axis momentum. So here consider this is equation 3. As we got that p square equals t equals to p square upon tm, p square equals to 2mt. We know that total momentum must be p square can be replaced with px square, py square, pz square. So I can write this equation 3 as px square plus py square plus pz square will become equals to 2mt. So I can also write the term t must be equals to px square plus py square plus pz square upon 2m, isn't it? So just we are replacing here the term p with px, py, pz. So this you consider as equation 4. So now you can substitute the value of this 4, equation 4 in equation 1. What is the equation 1? The equation 1, the total energy is the kinetic energy plus potential energy. So here the term kinetic energy T we got as in equation 4, the value is this one. We substitute this value, E is equals to px square plus py square plus pz square upon 2m plus v. So here I am just substituting the value of T from equation 4 in the equation 1. So this is our equation 1. So we will get this one. But using postulate 2 of quantum mechanics. So according to postulate 2, what is postulate 2? Every term we need to represent in terms of operator, right? So the momentum normally can be represented as P. But in terms of operator, when you represent, you have to write it as h by 2 pi I dou upon dou x. If you write in terms of momentum in y-axis, so you can write h by 2 pi I dou upon dou y. If you are considering momentum in z-axis, so you can write h by 2 pi I dou upon dou z. So here we are going to replace each term in terms of operator form. You can replace px, py, pz in this form. So according to postulate 2, the energy can be represented in Hamiltonian operator, that is h cap psi equals to E psi. So everywhere we are going to replace the energy in terms of Hamiltonian operator. Rather than writing E equals to T plus V, I am going to write h cap is equals to T, that is kinetic energy plus V. So here the value of kinetic energy we already got. What is the value? That is h cap is equals to px square plus py square plus pz square upon 2m plus v, right? So here I am going to replace the px, py, pz values as we got this one. From the postulate 2 we got these values, right? All these values we are going to substitute in this equation. Consider this is the equation number 5. So when we substitute all these values, we get this equation. This equation considered as equation number 6. We are just substituting px as h by 2 pi I dou by dou x, py as h by 2 pi I dou by dou y, pz as h by 2 pi I dou upon dou z. And as we know that here I can be considered as minus 1. Here if we substitute this as minus 1, so the total value of this one, here you can consider h by 2 pi I is common in everywhere, right? So this term you can take it this side, so you can also write this is minus 1, so the minus term also you can take it as a common. So h cap will become minus, because here minus I will become as minus 1, and you can also write h square 2 pi square, that is 4 pi square, multiply with 2m. So 1 by 2m multiply with 4 pi square, it will become 8 pi square m. So I am directly writing, so here h square upon 2 pi I is common here. Here 2 pi I square whole square will become 4 pi square. So that 4 pi square multiply with 2m, it will become 8 pi square m. So I am writing directly 8 pi square m, which is common in everywhere. So apart from that, you also have what is that? Dou square upon dou x square, dou square upon dou y square plus dou square upon dou z square plus v. So since the potential energy is the function of position coordinate, so The operator for V is itself V only, it is not changing. So ultimately the H cap Hamiltonian operator can be written as h square upon minus h square upon 8 pi square m. You can replace the entire term with a Laplacian operator. As we study in the Laplacian operator, del square can be represented in terms of dou square upon dou x square, dou square upon dou y square plus dou square upon dou z square. So I am replacing the entire term with del square plus v. So this is the equation we got, right? Consider this is the equation number 7. So as we know from using the third postulate of quantum mechanics, we can write the Hamiltonian operator h cap psi equals to E psi, right? So you can also write this equation. Consider this is equation number 8. You can also write this equation. If you take this E term to this side, so h cap psi minus E psi will become 0. So this you consider as equation number 9. So the E value, so the Hamiltonian operator, we got the value, right? The h cap value we got from the equation number 7. So if you substitute equation 7 value in equation 9, so what we will get? We'll get h square upon 8 pi square m del square plus v. So this is the h cap value. Psi minus E psi is become equals to 0. So consider this is the equation number 10. So this equation 10, we can also rearrange this equation by multiplying each term with psi, and we can also write that is del square psi, this minus h square upon 8 pi square m plus v psi minus E psi equals to 0. And you can also write del square psi minus h square upon 8 pi square m equals to, this one if we are taking this side it will become as plus, so E psi, this term will become negative, so V psi. And you can also write this equation as del square psi minus h square 8 pi square m. So if you are taking the entire term to this side, so plus E minus V psi is common equals to 0. So here equation 11 can also be written in another form, that is if we want only the del square psi value, then you can write del square psi. You can take this entire term to the other side. So you can write this term, if you go this side it will become opposite, that is minus 8 pi square m upon h square E minus V psi. So this you can write if you want to find del square psi value. Or else if you take the entire term this side, you can also write this equation as del square psi plus 8 pi square m upon h square E minus V psi equals to 0. So this is the overall, any form you can write. So you can write in this form also. Consider this is 12 and this is 13. You can also write in this form also. Anything is fine. So this is actually the Schrodinger wave equation. Here we have to substitute the Laplacian operator del square value in the equation 12 and 13. We will get the final equation. So consider this is the final equation 13. So here del square value we are going to substitute del square, that is Laplacian operator value, that is dou square upon dou x square, dou square upon dou y square, square upon dou z square. If you are substituting this value here, you can multiply each term with psi, so you can get it the final equation, that is dou square psi upon dou x square plus psi upon dou y square plus dou square psi upon dou z square. Or else you can individually you can multiply, or else you can keep it at the end also psi. Both will be correct. Plus 8 pi square m upon h square E minus V psi equals to 0. So this is the common form of the Schrodinger wave equation on the basis of postulates of quantum mechanics. So this is the final Schrodinger wave equation. This is the entire derivation of Schrodinger wave equation, and this equation is the final form, and this is actually based on the postulates, that is quantum mechanics. We have used the second postulate, means every term we have converted into operator form, and also we use the third postulate, that is Hamiltonian operator H cap psi equals to E psi. So the Schrodinger wave equation is basically derived on the basis of wave mechanical postulates. Okay, so thanks for watching this video.